Gentlemen, welcome to revision of grade 11 trig. It's a first part of 3 that you'll be watching today in preparation for the final part of the grade 12 trigonometry. Some of you have seen this in class already. However, for a great bulk of you, I think it's been a while since you've done trigonometry. The test that you'll be writing later this term on the 9th of July, I think it is, will be on trigonometry. So this is a really good chance for you to start revising that topic. What we'll try to go through today is everything that you should remember from grade 11. So perhaps as we start, you should have a pen, pencil, notepad, calculator, possibly a formula sheet. I'd like you to pause this video and try to write down everything that you remember from grade 11 trigonometry. Okay, good. So hopefully what we'll be able to do now is you can give yourself a point every time I mention something from grade 11 that I think is important, and we'll see if it's on your list. First thing, the trig ratios. Most of you remember them by their other name, the abbreviated name, I suppose. That would be the following. Sockets over. Where sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. And so if we're looking at this right angle triangle specifically, we must notice that it has a right angle here. So we definitely can only use this for right angle triangles because that gives us the opportunity to speak about something, the hypotenuse. Depending on where we stand now, we'll get a set of ratios that describe each of those angles differently. So if I was standing, for example, in the corner that's related to A, then what I would have is a set of A relationships, all with A speaking about its own opposite and its own hypotenuse. The second set of relationships that we could look at is if I was standing at corner B, and the B relationships would have their own sets of opposites and adjacents. So if we do an example of one of these, if I was standing at corner A and I was looking for the sine of A, I would be speaking about its opposite and hypotenuse, so A over C, which is what we can see happening here. And all these other relationships we used in grade 11. There are the reciprocal relationships, but we really would only really deal with those to convert back into these original relationships. So for everything that you're going to be doing, try and remember sine, cos, and tan, and what we need is a place to stand and then what we're looking for. The second way we can speak about the trig ratios is in relation to their Cartesian plane allocation. So if we were standing at the corner that is indicated by alpha, alpha itself has a specific corresponding opposite angle. So opposite alpha would be this side, adjacent to alpha would be this side, and then what we still have here is the hypotenuse. However, in the Cartesian plane aspect, what we really have is when we're speaking about opposite, we're speaking about a y value, a value that goes up and down from the x-axis. When we speak about adjacent, we're speaking about an x value because it moves away from the origin. And instead of the hypotenuse, what we're speaking about is the concept of a radial arm, because this could be pictured as an arm that could be part of a radius that would go around in the circle. So each one of the trig ratios would have their own description based on the polar coordinates because we're on the Cartesian plane. So if we were speaking about sine of alpha, instead of opposite and adjacent, we could speak about it as y over r. For cos of alpha, we could speak about it as adjacent over hypotenuse, x over r. And for tan of alpha, we could speak about opposite over adjacent. And these then become what we use when we're describing the coordinates on the Cartesian plane. In quadrant 1, as you remember, everything is positive, so there aren't really too many issues that happen in this first quadrant. What we then saw, after having looked at the polar coordinates of all the trig relationships, is that each quadrant specifically has a space where its positivity is important. In quadrant 1, what we found was that they were all positive. They were all positive in this quadrant because all the x's are positive and all the y's are positive. So any fraction we created had a plus divided by a plus, and therefore everything was positive. In the second quadrant, what we noticed is that the only relationships that were positive were sign relationships. And that was important because in this quadrant, the x's were negative, the y's were positive. But what we knew about sine in this quadrant is that sine is equal to a y over an r. And since r is always positive, we have a positive over a positive. The other relationships, cos and tan, were negative in this quadrant. In the third quadrant, the x's were negative and the y's were negative. And so what happened here was we noticed that only tan came out positive, because tan quite specifically had a relationship where we had an opposites over an adjacent, a negative y over a negative x, and two negatives made a positive in this quadrant. Lastly, in the fourth quadrant, what we had was that only cos was positive. And that relationship came about because the x's were positive, the y's were negative. And if you pictured what happened with cos was x over r, and that had a plus divided by a plus. So what we really wanted to remember in our class diagram, and this is perhaps something that you'll write down immediately when you start any test, is you'll give yourself a little memory aid of ASTC, the class diagram, specifically worrying about the positivity of the original trig ratios in each of those quadrants. Building on from the class diagram, we then had to take into account what would happen if we moved off of specific axes. So moving off of this axis, which was 0 plus, could get us up to the 90 degrees. But from 90, we could come backwards, which would make us a 90 minus. We could have also gone forward, which would have been a 90 plus. If we got to this horizontal, we could have gone 180 minus. We could have gone 180 plus. Or for this next vertical, 270, we could have come back 270 minus. We could have gone forward 270 plus. And eventually we get back to 360. And again, it could have been 360 plus or 360 minus. And what was important was to look at what was happening to these names of the trig ratios off of the verticals. And so what we had was a set of rules called the co rules or co-function rules. When we worked off of the verticals, so here's a vertical and here's a vertical, what we had to take into account is to the other verticals on the other side is what are we placing where? And so what we notice, let's take this first one. If I wanted to put sine of 90 minus, if I put sine 90 minus, I'm putting sine into the first quadrant and everything is positive. So the output of this stays positive. However, what we had to do was include the letters CO onto the name. So those letters CO got added. If the letters CO were already there, then we removed them. So there was no CO in front of it and they stayed positive. What we saw from 90 plus is that if I was placing sine 90 plus, I'm putting sine in its own quadrant. It is the sine function quadrant. So if I put sine of 90 plus, the output stays positive because sine is positive here. However, we've added on the letters CO because the original did not have the letters CO. The tricky one, the one that always confuses the kind of situation, is what happens if I go cos of 90 plus? Well, let's first look at positivity. I'm putting cos where? I'm putting cos in the sine quadrant. If I put cos in the sine quadrant, it has to be negative. And then I remove the CO to make it negative sine theta. So this is the one that always really kind of gets guys a bit confused. When you put cos into the sine quadrant, it has to go negative, and then we call it negative sine theta. These same rules apply when we're coming off the 270. So 270 plus or 270 minus. I haven't really shown them here at the bottom of this. We don't often deal with them, but the same rules would apply, is that if you were placing the different trig ratios from 270 minus to 270 plus, you would have to take into account where are you placing that specific ratio. Is it possible for it to be positive or negative there? And then we either add or remove the letters CO. Now, even though this is quite confusing to have a negative angle, it is possible theoretically for us, if we started at 0, to travel clockwise around the Cartesian plane. Now, traveling clockwise actually takes us back 90 degrees, back 180 degrees, back 270 degrees, and we could go all the way back to 360 degrees. And so we could travel around a theoretical negative angle. But what is important, I suppose, to realize here is that we have negative angle relationships. So sine of negative theta just becomes sine of theta because you're placing it here in the fourth quadrant, and sine is negative in the fourth quadrant. Placing cos into this quadrant, so placing the cos one into this quadrant here, it goes positive because cos is positive in the fourth quadrant. And lastly, if we place tan as a negative angle into the fourth quadrant, so placing it here, it comes out negative again. And these relationships would stay for this fourth quadrant example. You just have to take into account how far back you've gone with each of your angles, but the rules would still apply. This quadrant here, they're all still positive. This is the sine quadrant, this is the tan quadrant, and this is the cos quadrant. What we then learned was that there was a set of special angles that we would see over and over again. And since all trig ratios are a repetition of a fraction form into decimal, we could actually get a set of special angles that we could learn off by heart. The ones that are really kind of difficult to visualize on a triangle would be the ones at the 0 degree or the ones at the 90 degree. So these ones we would just say to you, go away and learn these properly. So cos of 0 is 1, sine of 0 is 0, tan of 0 is 0, cos of 90 is 0, sine of 90 is 1, and tan of 90 was undefined. The others, however, came about through a construction of the unit circle, and depending on which method you've learned, either the fan method, the table method, or the triangle method, you would remember these yourself somehow. You have to have some way of putting this down on your test paper. This is not given. So again, almost everything I've written about here today, including this, is information that you have to go into your exam with, ready to use. How do we read off of these tables? I suppose the easiest way for us is to say, well, if we wanted to stand an angle, if I was standing at 30, and let's say we wanted sine of 30 is opposite over hypotenuse, so we get 1 over 2. I can read that off of the table also, because sine of 30 is 1 over 2. So each of these relationships is quite important for us. The two special triangles that we could draw were this 30 and 60 special triangle and the 45 special triangle. Another thing that I suppose you could notice about this is that when they say without a calculator, this is what they want you to use. So this is really like a big, whenever they say without a calculator, they're telling you that either everything cancels and it becomes quite nice, or you're going to convert a trig ratio into a special angle fraction. So this is really what they're doing when they say without a calculator. You might ask yourself, how would you know if I've used a calculator? Well, in a test or exam, we're not really going to specifically know, but what we will notice, I suppose, is that your calculator does not like to have square roots in the denominator. Your calculator will rationalize the denominator. So what we will definitely see is any time that you used your calculator when you shouldn't have, you will probably not have a square root in the denominator. Is that right or wrong? We really don't mind, but it is important for you to know that that's what's happening behind the scenes. The next set of important grade 11 concepts that you would have remembered should be the trig identities. And the first identity would be the tan identity, where tan theta is sine theta divided by cos theta. This would probably mean that anytime you see the word tan in a question, you could convert it out into this fraction form. Second identity, which is shown on the formula sheet, is the sine squared plus cos squared equals 1. So this quotient identity and the squares identity are given for the most part, but I think that's what's important about these is to look at what their other forms could be. So another way of writing out, let's just label these quickly. So this one's the quotient identity, and this calls from the square identity. If I rewrote the quotient identity just for a second, what you could see is another way of writing it would be that if I multiplied both sides by cos theta times tan theta quite quickly reduces just down to sine theta. So that's something that you could learn off by heart if you wanted to. It's quite easy to prove also. Another form of this could be that you could see that cos of theta would be the same as sine theta divided by tan theta. So anytime you get any of these weird products of cos, sine, and tan, or any of the times you get this quotient, you could convert quite quickly to a single trig ratio. For the square identities, we could do something similar. For the square identity, if I took the original square identity and I divided through by one of them, so if I divided through by sine squared on everything, I could get another set of relationships. So sine squared divided by sine squared would just give us 1. Cos squared divided by sine squared gives us cot squared. And 1 divided by sine squared is cosec squared. That would be one form of this. We could have also divided everything by cos. If I had have divided everything by cos, then sine divided by cos would give us tan squared. Cos divided by cos would give us 1, and 1 divided by cos squared would give us sec squared. So anytime you see a square in an expression, you probably want to convert it back to one of these square identities, sine squared plus cos squared. Again, what we'll notice, I suppose, is that anytime you see a 1 in trig, it probably doesn't mean 1. We can write it out as something else. What I've done on the right-hand side here is just rewritten them where we've made one of the terms a subject, so sine squared equals 1 minus cos squared, etc. And just as a backup, you could also see them in terms of their square root identities. But this is really just as a super backup in case you couldn't figure out anything in the square form, we could do the square root form. Okay, let's go through one of two worked examples today. Determine the value of this expression without using a calculator. What does without using a calculator mean? It means we're going to be using the special triangles. Even though we can't see them right now, we're going to be using the special triangles. So pause this video and give it a try yourself. Okay, so let's see what you would have done. 420, 225, 45, and 315. Can we rewrite those numbers to either be a 30, a 45, or a 60? I think we can. So let's take the cos of 420 first. Cos of 420 would be the same as 360 plus 60. Sine of 225 would be sine of 180 plus 45. What we saw for the negative angles already, as a multiplication, is that cos of negative 45 just becomes cos of 45. And these would all be divided by tan of 315. Now tan of 315 would be written as tan of 360 minus 45. What this expansion now gives you is saying the following. Where are we going to put cos and what are we going to put there? Where are we going to put sine and what are we putting there? Where are we putting tan and what are we putting there? So each one of these could be refined further. Cos of 360 plus 60, 360 plus 60 is in the first quadrant. In the first quadrant, everything's positive, so we're going to have cos of 60. 180 plus 45 is the third quadrant, and sine is negative there. So that negative, along with the negative in front of it, the coefficient becomes positive, sine of 45. Cos of 45 just stays cos of 45. In the denominator, 360 minus puts us into the fourth quadrant. Tan is negative in the fourth quadrant, so we've got negative tan of 45. At this point, we've got 60s, 45s, so we can use the special triangles. I've written them on the right and left-hand side here. So cos of 60 is adjacent of our hypotenuse, so that's a half. Sine of 45 is 1 over root 2, and cos of 45 is also 1 over root 2. That's going to be quite nice, it'll tidy out. And tan of 45 is just 1, so we've got negative 1 in the denominator. What we then get in the numerator is a half plus 1 over root 2 times 1 over root 2 is also a half, all divided by 1, so this whole answer is going to be a negative. And so what we get then is half plus half is 1, 1 divided by negative 1 is negative 1 as a solution. The second type of question you would have done a lot of in grade 11 is proving a left-hand side and a right-hand side. So pause this video using pen and paper, try prove the left-hand side, sine squared alpha minus tan alpha minus cos alpha in brackets, multiplied by tan alpha plus cos alpha in brackets is equal to the fraction cos squared alpha minus sine squared alpha all over cos squared alpha. Okay, so I hope you've had a chance to try this. What you want to avoid is using the equal sign. We cannot treat this as an equation. What you'll get is 0 equals 0. And because this is true, they told you to prove this, it is going to be true, you're going to end up with 0 equals 0. The only way we can approach these questions is to split them into a left-hand side part and a right-hand side part. So we don't often need both, but let's just set up our equations in the meantime. So for the left-hand side, what can we notice? For the left-hand side, what we can definitely notice is we want to get rid of these brackets. So let's keep the sine squared first of all, and let's FOIL out these brackets. And the brackets are in the form of a difference of two squares. A minus b, if you can picture this, a minus b, and a plus b. And we know that if we FOIL those out, we would get a squared minus b squared. So what we then get for our brackets is tan squared alpha minus cos squared alpha. What we want to then do is distribute the negative into the brackets. So what we get then is sine squared plus cos squared. I'm rewriting this and you can see why, minus tan squared. And sine squared plus cos squared is 1. So we land up with 1 minus tan squared alpha. That's about as far as we can go on the left-hand side. Can we now make the right-hand side look like this? Well, I think this is actually quite a nice one because we've only got one denominator on the right-hand side. So let's rewrite it with a split denominator. And almost immediately you can see the solution coming out. Because cos squared divided by cos squared is 1, sine squared divided by cos squared equals tan squared. And so what we have shown is that the left-hand side does equal the right-hand side. I hope you've remembered a lot of this work. It is going to be important for the assessment that you're going to be doing coming up. moving on from today, we're going to be adding on 2 new components that are important for you to learn for the grade 12 components of trigonometry, the compound and double angle formulas.